Hey, good afternoon and Happy New Year, in case we haven't seen you before. Welcome to our first GReTA seminar this year. So very happy to have Manfred with us today, Professor Manfred Nagl, who, in case you don't know, is one of the people who started it all. So we probably wouldn't be here without him. So he started working on graph transformation in the graph grammars, probably as they were called at the time in the early 70s, when there wasn't an established research area as such, but sort of the first ideas about graph grammars came around, I think, in the late 60s, and then Manfred Nagl was one of the first to develop them more formally, and in particular developed ideas about what it means for graph grammars to be context-free, for example, and sort of balancing the kind of results that you get for context-freeness with expressiveness. So that was the first sort of major part of the theory there. And then later, he used that sort of technology in order to develop, I mean, what you probably would call model engineering tools today. So tools to support software development in multiple use with different models that needed to be kept consistent and integrated. And also in his group, then the first practical implementations of graph transformation, and the kind of children of these tools are still with us today. So that's an important legacy there. But apart from that, and more recently, he became interested in Gothic architecture, as you can see from the nice picture here, and in the relationship of that with, I guess, engineering methods in informatics and maybe in particular software architecture. But I let him explain that in more detail because that's what he's here for. So please, Manfred.
Okay, thank you. Raiko, thank you for the introduction. And indeed, so what I'm going to tell today is a bit outside of the usual pattern for the GReTA seminar talks. It is about intelligent design in times of Gothic churches, 1200 to 1500 on one side, and in informatics or engineering disciplines today. Okay. I aim to have three topics after my talk. The first is that you appreciate what the people have done long time ago, as I said, 500 to 800 years ago. Especially if you think that there were no means we have today at hand, like a computer, a file system, or CAD system, and so on. So everything they did in their heads. And furthermore, I would like to point out that there are very nice relations between design in architecture on one hand, taking the example of Gothic churches, and design in informatics and engineering of today. These are the three goals I have with my talk. Okay. But now something, as I said, it's very strange. If you make the pointer visible, nothing is working. Okay, so why did I do this kind of might be strange things? The reason is that in an age of 16 or 17, I gave a talk at school, at secondary school, about Gothic churches. And there was some ignition, some interest in these kind of buildings, and which still is viable today. And as you already indicated, we did a lot of work in my group, and you see the names of the persons who collaborated in these topics on tools for software development or mechanical engineering, chemical engineering, and so on and so on. And after the time of my retirement in 2009, I had some time to work on this topic, and I was not pressed by something like H-index or something like that. So I could just work on this topic, okay? And after software development, chemical engineering, there are also other topics like communication, e-home, process control, authoring, civil engineering. There was I collaborated with two people from Poland on this topic to use graph rewriting and intelligent ideas for which make CAD tools more semantical. Okay. And now I'm trying to tell some topics which are contained in that book of 2019. And the outline of my talk is the following. First, I have a section on Gothic style. We will not be an expert in Gothic styles afterwards. Then we have a part, the CAAD part, computer-aided architectural design on the construction of Gothic churches within a computer. And then we have the main part of today, relations to informatics, especially addressing similarities and differences, processes, architectures, algorithmic design, parametric design, reuse design, and class design, or the design of classes. And finally, I would like to make some remarks at the end of my talk, what we have learned, and outlook, and possibly have some further slides for the discussion if you ask for them. Okay. Now, summary of Gothic style. The Gothic style is a perfect unification. On the other hand, one side is it has a background in theology and philosophy. The so-called scholasticism, which was invented around 1400, and they try to show that there is a unification or a good interplay between theology or belief on one hand and ratio or mind or logic thinking on the other hand. And the people argued for some time that the Gothic churches are good examples to explain this. Then Gothic churches have a big representation. They show the power of religious or political or economic units like a bishop or a nobleman, a famous person of the chapter, or the noble person of the area, or in some cases also of the king. The idea is to glorify God with a new kind of temple, which is looking completely different of what we see in the Romanesque era, where we speak about the fortress and castle of for God, and now we speak of a new kind of temple, which has a completely new shape. Namely, the churches are very high, they are slim, and they are very light. So big windows are offer the possibility for the sunlight to get in. The style is revolutionary. It is filigreed and harmonic, as we are going to see. It uses completely new forms and details, like we are introducing in the first part. And what is also important, like all other styles, they are European movements. So Gothic churches you find everywhere in Europe, but you also find in different countries different occurrences of Gothic churches. There is some similarity, but if the two examples which I mention specifically, namely France and England, they show that the idea to realize Gothic and to design Gothic churches is different. Okay, now let us start to introduce some basic terms. Here we see the Reims Cathedral. We see the main house with the nave in the middle and aisles at both sides. We see the transept. This is here, the transept. Now I try to make the other kind of yes, the transept, which is here in the middle, the crossing of the transept and the nave, and the choir here. The choir has a central part and an ambulatory which go around, and a second ambulatory in the case of Reims, which is starting here and then continues as a ring of chapels. Okay, then we have the west front, the west facade with two big towers. Okay, this way it goes. Here we see, look into the Cathedral of Reims. We see the high nave. We see the wall, the main wall, which has three parts: the column and the arcs on one hand, the triforium, the big windows on top. We see the ribbed vaulting, and we see the aisles here. And we look to the west. We see these big rose windows of the entrance side of the church. The outside of the church is at least as interesting. It has the construction, very refined construction in order to perform stability of the church, because this very high nave makes much stress to go outside, and this has to be caught by these buttress construction here. Okay, and okay, the next is we go in the church, in the main house, and we see that this is the nave, the two aisles. We see the construction outside, the roof, and so on. We see that the huge windows here of the main house, and here the windows of the aisles. And we see that the construction, the stability, is based on columns and connected columns. On the one hand, by the vaulting, the different segments together, and by the buttresses to these columns on the outside. So this is completely new, and this guarantees stability in a static sense, but it also guarantees stability in a dynamic sense. We are unfortunately in World War I and II. Some Gothic churches have been destroyed, but they are much less destroyed than the surroundings. If you look on the pictures of, for example, Rouen or Freiburg or Cologne and so on, you see there is no building standing in the environment, but the churches are damaged, but they are still stand up. Okay, that is due to the fact that these construction of columns which are connected guarantees some flexibility against big blows. Okay. Here we see a picture of France, and the famous churches are in a circle with a diameter of about 200, 300 kilometers around Paris. I'm not going into these many details. In the talk, we will speak about Notre Dame de Paris on one hand, and another church in England, and of course in Reims. And there are three churches which have a political importance. This is the church north of Paris, where the Gothic style was invented, and which afterwards was the place where the kings of France were buried. Then the Paris, Notre Dame de Paris, this was the church of the king, and Reims, which is the church where the kings were crowned. Okay, it makes me nervous that okay, then we have, oh, this is one too much. Here we have the history of Gothic churches in France. It starts with Laon. Laon is a Romanesque church, but you see that the structure of the west facade is nearly the same as of the Gothic churches following. Then we have early Gothic church. This is Notre Dame de Paris. This is the Cathedral of Reims. You see that the refined structures grow from Notre Dame de Paris to Reims, and we also see that in the late Gothic it is even bigger. You see, this is the choir of Beauvais. This is the church with the highest nave in the choir, or the highest nave at all, 48 meters high, 48 meters high. This is a beautiful choir, the nicest, the most filigrane, the slim and high choir you can find in the world. And the method in order to find out how to build high and slim churches was based on trial and error. So they tried a bit and tried a bit. Some were stable, some not, and they learned. And in Beauvais, they learned a lot of building a high choir, but the church was not stable. So in the crossing, there was a huge tower here which collapsed and was destroyed the rest of the church. So what we see today is only the choir. Okay. Now we switch to England, and in England again we have a series of very important churches, and we have three churches again which have political importance. This is the Church of the King, Westminster Abbey. This is Canterbury, the Church of the Primas of the Anglican Church, and this is York, the Church of the second person of the Anglican Church. Okay, and we see a lot of these, and in order to give an impression at the very beginning, the French churches are looking much slimmer and higher and elegant, but you find no place in the world where the Gothic churches have such a variety than in England. This is very important to know. Okay, in English, we also have different periods. It started with early Gothic, which is called Lancet Gothic, you see, because that reminds on the top part of a lancet, these windows. Then we have the decorated style, which is high Gothic style in France or elsewhere in Europe. And we see the late Gothic style, which is called perpendicular because the vertical lines are emphasized. Okay, and then we have another Gothic style, which only exists in England. This is Tudor Gothic. England is the country where nearly all churches are Gothic, either from the time from 1200 to 1550, or from the time afterwards in the so-called Neo-Gothic era. Okay, so they liked Gothic style very, very much. This is York Minster, and you see in one glance that is looking quite differently. It is extremely large. It's not so high. It has a massive tower at the crossing. And you see this, it's a rectangular choir, and this choir has two different portions. Okay, so you see by one view that it is not a French church. It is an English church, which has specific characteristics. But as I said, nearly all the churches look differently in their structure. Okay, Norman Minster is also important because it was a reconstruction of a Norman Romanesque church, a huge Norman Romanesque church. You see here the base of the new church, and you see here the occurrence of the old church. You see they are nearly as big. The Gothic church, the Romanesque church, is nearly as big as the later Gothic one. Okay, and it was typical. This church, the Romanesque church, the Norman church, was replaced piece by piece by Gothic parts. You see here the first part, that was the transept here, which is replaced. You see the Romanesque church here, and this early Gothic, Lancet Gothic part of the transept. Okay. This is stupid. There should be another. I think I put it out. I go back. Okay. Now we enter the part where we, the CAAD part, where we make virtual constructions of the Gothic churches, okay? The first is, this is the ground plan of the church of Reims. And the first part is that we construct an element which we call a travée in French, or also in the special language of Gothic churches. You see here it has all elements of the main house, namely the nave, the aisles, the columns, the wall which has 3 parts, and the buttresses outside the roof, and so on. And this travée, we were going to learn later, can be constructed by a parameterized element by fixing the different parameters, okay? And we put this travée into the ground floor, and then we multiply it by 8. And then we have the main house. Then we take this travée here and modify it. We add another aisle here to form the first part of the choir. Yeah, the buttress is a little bit more complicated. We do it into the church. There are 2 elements of this kind. The next step is that we take this element again. We take the half of it and take here this line and take the half of it and let it shrink to a point that we get a triangular segment. And we add a chapel here. And this element is put here and is multiplied 5 times. In order to give the choir, okay? Then we are constructing the crossing, which is looking a bit different, so we have more to do, to modify, but we can at least use the elementary elements again, which is then put into the transept. We have the 2 elements north and south of it, and we take the west front, the north front, and the south front, which is a little bit different on both sides. And then we are constructing the west facade, which is also where we only can take some elements of the already constructed elements. And we go to the tower. You see again, this is a completely different thing. We have different floors here, where we can use elementary things like windows or columns and so on, but the rest is constructed. We put it on the west side and we mirror it on the other side, and this is the church. Okay, so this is the church in total. You are looking now from the northeast side, and we see the choir, the main house, the towers, the crossing, and the transept. Okay, this is the inner side. So we look from the transept to the west. We see the 2 rows windows, and we see the nave, the aisle on left and right. And this can be now, we have a scene. We are walking to the west on the first floor to the rosettes on both sides. We turn, go down. And in the north aisle, we go forward to east. We pass the transept. We continue in the choir. We look to the west. This is here. We look to the west. Okay. We continue going through the choir. We are in the crossing now. We turn to the north. We turn to the south. And now we go out of the church in backward sense. We go out and go on the north front and see now the west facade. Okay. No, that's not what I wanted to do. So whenever you take some of the buttons, which this has an effect you would not expect. Okay, here is now the Minster of York in 3 different parts. So this was early Gothic part, which was replaced first. Then came the main house with the towers here. And then came the choir, this huge choir, which has an inner part and an east end here. So, and there is a chapter house, which is also very specific for the English churches, the chapter house. Again, a view on this, on that church, not so high, but mighty, a mighty church, a huge tower at the crossing. And we have studied also different churches, the Holy Roman Empire, but also in Spain, Italy, Netherlands, Poland, in Czech Republic, in Austria, and so on and so on. So they all are different. They share ideas of some elements, but all are different. I would say Gothic is a European movement because you find churches everywhere, but every country has different occurrences. And that might be the way how Europe is working and should work also on a political level. Not a centralistic command from one place, but a different movement in a direction which is similar. Okay. So we have also done different modifications, for example, of Reims, of Milan, of the Church of Duomo of Milano, for example, showing the Duomo in a only Gothic way, because the Milano Cathedral was on the very end of the Gothic era, and it also has elements of the Renaissance and of Baroque time. And the question was, how would it look if we would have finished that in a shorter time, in the time of Gothic? Also, we have modified Cologne. That was only not done in order to show that we can improve these churches. That was only done to show that whenever we have a model of the church inside a computer, we can play around. And this has an importance, for example, for building history reasons. You can explain how a church has modified over the different centuries. Okay, this is and there are many different other types of church. You can even by this approach model mosques, and you can even model modern buildings. And for these modern buildings, the importance is even higher, because to have an original design which is just for this church is not so important anymore. It was very important in the Gothic time because these different countries or different noblemen or chapters competed against each other to build the brightest church on earth. Now I come to the relations to informatics. And that means, especially to software engineering in my talk, but you can see that it's quite similar if you take an engineering discipline. It's quite similar. Whenever you have different systems which share some characteristics, you can apply the same kind of modeling, the same kind of design as we have shown here. So what you need are similarities, structural similarities. What you need is to make use of reuse and also of adaptation. We have algorithmic design. I'll show an example afterwards. For example, for a Gothic tracery window. Okay, we have parametric design. We have seen, and we are going to explain for the travée we have seen on the floor for the Cathedral of Reims, and we can make a design of a class of buildings, and then construct different representatives of this class. Okay, and we can think about tool support in direction of reuse, algorithmic, parametric design, and so on, which, as far as I know, was never a point for people who worked on tools. Okay, now back to the cathedral, to the Cathedrale of Paris, Notre Dame de Paris, and you can see it was started in 1163 and ended in 1345. So this is nearly 200 years. And if you also look on some kind of modifications made in the 19th century, then this construction period even could be found in the 19th century. For example, in the Big Fire, this small tower at the crossing was built in the 19th century by a very important person of history of buildings. Okay, now I take the assumption that we are trying to build a church of this type, or which is quite similar to that church, 3 times one after the other. What is the effect? But before we go into that discussion, I would like to show that the way how Gothic churches have been built in France or England and so on follow what we call today the agile development, and there is a manifesto of 4 different points which we can find in the way they have been used in 1200, 1300, 1400, without knowing of the manifesto, of course. The first is, whenever you construct difficult things, react on changes, which is more important than following a plan which was fixed beforehand. That is not possible at Gothic times, because churches were constructed in times which lasted a few hundred years. The longest example is Cologne on one hand and Prague on the other hand, where the construction was finished in 1870 in Cologne and 1915 in Prague. And both started in about 1250. Okay, so a huge time. You cannot make a plan which is still valid afterwards, because even in Gothic time, the style changed, as we have seen. Okay, then the cooperation with the customer, the person who gives the money, is more important than the contract. You must be flexible. There must always be a connection, a talk between these 2 different parties. And the individuals and the interactions are more important than fixed processes or tools. Okay, so there must be a place for individual action in order to make an element which is new in that time. And the working software or the final church is more important than documentation. Okay, these are the 4 rules of the development manifesto, and I detected an article which went in this direction, and I worked on that and continued that argumentation in the book. And why was that so successful? Although the construction needed hundreds of years, nobody would expect that something which is coherent and looking very nice comes out after hundreds of years of construction. And it is mostly because the 2 roles have been lived in an extraordinary way. In German, it's called the Baumeister. This is the person who gives the contract, who gives the money, who has the idea to build the brightest church on one hand. And the Werkmeister, this is the architect, but also on the other hand, the person who is doing the control for the physical construction. And they worked very closely together. My statement is, if that would have been the case for complicated buildings of today, all the very difficult cases would not have happened. Think, for example, of a concert hall in Hamburg, or think of the airport in Berlin, or think of the university hospital in Aachen and so on, which finally showed that you cannot plan a complex building without spending something like pi half or pi or 2 pi the money you have planned. Okay, so this is a very important, which is evidently violated today. And whenever we plan something complicated, we should go along with these statements here. The next is architectures for buildings. There we have different views. We start with a conceptual picture, which is often made still today with paper and pencil mode between the person who is giving the money, for whom we build a house on one hand, and the architect on the other hand. Then the architect makes a plan. The plan is a 3D sketch and different views from the different directions. And he makes floor plans. For example, here a simple floor plan, which is then approved and which is then made detailed by dimensions, but also by things to be placed in different parts and so on. And furthermore, we have different extensions for piping, for electricity, for roof construction, for the basement, and so on and so on. Okay? And even in big houses, we have the usual use that you place certain rooms at one place and together with other rooms. And we have an evacuation plan, a dynamic use, on the other hand, in the case of fire, for example. So what we see is we have different granularities from sketches to details. We have different aspects, as here the floor plan or the outside structure. We have or the extensions. We think about static use and we think about dynamic use of the building. Okay, and for any architect in the world, these different plans are completely clear. That we miss in software engineering. People speak about different fragments where it is quite unclear how these different fragments are put together and form that what is later on a big software system. Okay, the same what we have found here for buildings, we find in software engineering. For example, the architecture of the multi-phase compiler, who has a different certain structure. There is one component which first activates the scan, the parse, and so on and so on. These are specific for the language, and there are components at the bottom which look for that the data can be exchanged from one of these phases to the next. We find simpler components here and more complex components, which we call subsystems. We find details for this architecture here, like, for example, the export interface or structural relations between the components. We might have further extensions, not in the case of the compiler, but in other cases for concurrency, for distribution, for efficiency transformation, and so on. And we might have the construction of these different parts. For example, scan. In the first run is built by just programming scan. In later forms, it is built by having a table-driven approach, by having a table. And even in later forms, the table is generated by a program from a specification. Okay? And we have a usage of specification of runtime, usual behavior, exceptional behavior, and so on. So the different views, the different granularities, and so on, this is also the same, but in many of the approaches for architectures, we miss that these different fragments can be seen as parts of one whole, and it are easily understood by other persons. Okay, so what we see here again is we have not just painted the cathedral here. We have analyzed the structure and we have made a structural build. We have tried to make use of reuse, for example, by multiplication, by these kind of travée structure, which is parameterized by different parameters, as we are going to learn. Okay, so it was a quite intelligent way of construction of the design, and later on also of the physical construction, because you can build certain things which facilitate the physical construction, then you can apply it because there are different parts which are looking quite the same. Okay. The same idea is we have in the multi-phase compiler, we have a global scheme here on the very course level. We have different components, one for controlling the different phases, and on the bottom side, different components which look for exchanging the data we have between the phases. So this blue part is the overall structure. These red parts are the parts which can be used for any compiler which is working in the multi-phase way, okay? And the green parts are the specific ones. At the next level, we first start with programming these specific ones, and we finish with parts here which are generated from a specification. So again, a quite simple approach to make the design, okay? Now, I would like to, this is showing that the effort, if we make the same, very similar church, is shrinking from time to time. I would like to skip this argumentation of these 2 or 3 slides and continue here with a new idea of algorithmic design of a tracery window. This is the so-called Reims window here. So it has a flower-esque part here, and it has 2 different pointed arcs below, and all embedded in one pointed arc. This can be constructed in a very simple way by knowing only the breadth here of the place where the window has to be embedded. Because you take this as the radio, you take this as the center of a portion of the circle with this radius, and you find the point where you have this point, and in an analogous way, this point here, where you have to draw these circle parts, then they have to the outside figure. Then under certain 30 degrees, you find this point here. You can draw the circle. You can easily find the parts where these 2 pointed arcs start and go below, and so on and so on. So this is a very simple algorithm in order to make a design. This is much more complicated in late Gothic times, where you have these so-called flamboyant windows. Okay. Here you have the Travé example of we have seen for the construction of the Reims, and there you have different parameters. So first you determine the geometrical parameters. For example, from the roof to the base, we have this height for the 2 side parts together with the roofs, and so on, and this breadth and this depth, and so on. The next step is to define the zones. Here, the arcade zone, the triforium zone, the window zone. Then the next part is to define the different parts where the structure, the elements start and end. For example, here for the vault is starting here, or here is the column, here is the triforium starting and ending, and so on and so on. Then we put different details and forms into that plan. For example, the form of the buttress on one hand, and the form of the windows here inside, and so on. We finalize it by different detailed structures, and then we have the Travé we have seen beforehand. Okay, so you see we have different parameters. Geometric parameters for the outside, geometric parameters for the zones, geometric parameters for the beginning and ending of structure elements, the form of these structure elements, and the details. Okay, And then we have the corresponding travée, which is used multiple times in order to form the main house. So this kind of approach is especially interesting for classes of churches. So we have shown it here for the classical French cathedral. Also in France, there are churches which are not built according to this class. Okay, for example, Albi in Aquitania, there are churches with round roofs and so on. So the overall plan is fixed, and we can give a deep characterization of the class which you regard. A deep characterization. So the similarity of the representatives in that class is very strong. And that makes it possible to use these kind of intelligent ideas. Okay, we have seen there are quite different parameters like length, height, for the relations, for the number of ships and bays, for the elements we put into the design, for the structure, the form of the structure elements, and so on and so on. So making this way, you can construct the same church multiple times and end after 3 construction shapes with a design which is completely ready. There's nothing to do. But this was not the way Gothic churches were constructed, because there was a competition between different places. Everybody wants to have the nicest, the brightest church. So it's not possible to make the same church multiple times. But this kind of principle here can be used for modern buildings. For example, for office buildings, for hospitals, for Aldi local affiliates, for football stadiums, and so on and so on. And then this tremendously accelerates the construction of the church, either on the design level or on the physical construction level. Okay, this sketches tool support for this kind of reuse or algorithmic or parameterized construction, where we have, as we have seen, we have different levels. The whole building, building elements like the main house, the choir, and so on. Complex element like the travée or the wall of the main house, and structure elements like a column or a window, and so on and so on. And after constructed these things, and they are used to be very similar, you store them in a data fragment storage, either on object level directly to use, or on type level where you say, I have to fix certain parameters and then make to instantiation and then to use that instantiation. And at the same time, if you have constructed something, you can look on the log what you did and construct something like a process fragment storage and put it again into some kind of storage here. And then the design would look that you start up, do I find the right elements here? Can I use them? Can I modify them? Can I use for this modification fragments of these processes here? And afterwards, if I am successful, I put it again into this data fragment storage, and if the process was interesting, in this process fragment storage. And the different activities we have here is look up here or here, to compose here, to adapt, to modify, to multiply, and to store. And the parameters are again listed here. So they are specific for the item class, for they are corresponding to the structure, to a geometry, selection of topics I would like to implant, and multiplicity, and so on. So this can even be extended in my lecture idea on software architectures. I distinguish between reuse on 2 different levels, namely deep reuse, if you use an approach like this, where you are doing, after some time, you're doing the process completely different, or flat or shallow reuse, which starts, you do the same thing and you have your knowledge in your head. Or you do the same thing, take the last design and modify it, okay? And whenever you would like to go from a design which is only a shallow design to a deep design, there also might be some helps necessary in order to make this transition. And this is something like an integrated tool support for intelligent architectures. I have not seen up to now a paper which shows something in this direction for reuse arguing for a tool support for this kind of approach. Okay, now we go to the summary part. The Gothic style, I think you accept, is highly sophisticated. It's not trivial. What people did in 500 to 800 years ago is highly sophisticated, elaborated. We have to bow for these people, and we should remind that at that time there was no study program for architecture. There were craftsmen who developed from step to step, who learned by doing, and finally built such beautiful things we admire 800 years afterwards. Okay, the structural elements, there are structural elements allowed to build high, filigreed, and statically solid churches. We have seen the pointed arches, there's columns, the buttresses, and so on. The filigreed and the high buildings where much of the light goes in is belonging to the big windows. So if you look on the walls, you find more windows than openings of the wall. Okay, they have a tremendous tradition in France, in England, in Holy German, in Germany, or beforehand, the bigger part, Holy Empire, Roman Empire, and in all the countries we have in Europe. The virtual construction of historical buildings by a parametric design using CAAD delivers new aspects, even to think about a tool environment for software for deep reuse. That can be supported, but nobody did. And if you look to industry, you find very, very seldom examples of this deep reuse. They mostly use these shallow reuse forms. Okay, the construction is interactive, inside out, and parametric, sometimes algorithmic, with various forms of reuse. There are different parameters here, as we have learned, and there are similarities to software development processes: build, modify, reuse, generated. We have tried to make clear both the two examples, for example, Reims on one hand, and the Paris Cathedral on one hand, and the Compiler Cathedral on the other. And there exist various relations to software architectures, as we have seen. Okay, now this I would like to skip, and I go to the open problems. We could do much more research about classes of Gothic churches. For example, we did not cover all French churches. Within France, you have at least 3 subclasses. That is the subclasses more in the area of Normandy on one hand, or the northwest part of France, or in the southwest part and the central part on the other hand. You could work on characterizing these subclasses, for example. Or this is even a more difficult task in the case of the English cathedrals, because they vary from every church to every church in the structure, forms, and so on. I have some examples which I can show you. Then you can determine the variations within a type and between different types. You can use it for a posteriori construction of historic churches, which allows a new introduction of churches, because you can animate the way how they are built, different parts. Please remember the different parts of York. There is a translation of virtual construction to other architectural periods. For example, the Romanesque style is much easier. What I've shown can also be applied to Romanesque style, can also be applied to the Baroque style, but not for churches, more for the form of castles. It can be applied for mosques, and especially it can be applied for modern buildings. Now, I come back to the very few remarks to graphic writing. And whenever we try to find out, can we replace now informatics by graphic writing? So could we, in our argumentation, take Gothic churches and make a comparison to graphic writing? And for me, there are three different questions. The first is, we have used similarities on architecture level. And the question is there an architecture for graph transformation systems? I do not speak about the tools which support graph transformation input or evaluation or execution and so on. I speak about how a design is made using graph transformation. And I'm not sure whether such an architecture exists at this level, that we can make sub-specifications, small parts, big parts. We can try to define the interface of the sub-specifications. We can try to define the relations of the sub-specifications, and so on and so on. The second question is, can what we have shown here use the similarities of ideas, methods, processes, tools for algorithmic parametric design, reuse design, design of classes, and so also be used for graph transformation systems? This is another question, and I do not think that many people have thought about this problem. Can we support to design graph transformation systems by these ideas? And the third question is, if we have an application, for example, the design of Gothic churches, can this be directly done by graph transformation systems? And we can go a little bit deeper in these questions in the discussions, but I cannot offer deep ideas corresponding to these questions. Thank you for listening, for your for the time you spent, and for the patience you have, and I'm looking forward for your questions.
Okay, well, thank you very much, Manfred, and yeah, very interesting. So I may start and then maybe see what other people want to say. So first of all, I have to say I find it very interesting that I'm taking your word for it. So that the state of the art in architectural design in buildings doesn't include the things that you described, like
only implicitly. So they make a lot of reuse. If you, for example, for me, if I see a building which is built, let's say from 1850 to nowadays, I can decide that it is building in a period of about 5 years. And this is due to the fact that they made a lot of reuse by taking ideas of other people, but they made not reuse in a systematic way. So reuse is very common, but not in a systematic way.
No,
for some buildings, it is different.
It doesn't surprise me, obviously, that in historical buildings you have that, but I would have imagined kind of more recently, since sort of automated sort of CAD tools are on the market, that architects sort of use these kinds of methods to basically construct buildings in the way that you describe, because it seems, well, I guess once you're presented with it, it looks like an obvious idea. Maybe it's obvious to us because we are used to those methods, but so just a statement. So I'm surprised that this doesn't actually exist, or that it is not actually relatively common.
So these ideas are not very common, and they are not very liked in architectural conversations because they fear that their jobs disappear.
Okay.
Yeah, this is the way. The reason behind they use for many time, a long time. They use this kind of reuse, looking on the colleague what he's doing and doing the same, but not making use. Some special companies might do that. For example, there is a special company in Aachen which constructs, which designs football stadiums. Mm-hmm. And if you look on the central part of a football stadium, you can make one design for a stadium for, let's say, 100,000 people to sit down, which is completely the same than in another stadium, which looks completely different. Okay, or you look for this kind of design, go to the Roman examples. Where, and if we go, I remember the time where I heard an opera performance in northern Italy, in what is the name? Romeo and Julia. Andrea, help me. Verona, yes, Verona. And I have been very surprised that getting in like 30,000 people and out is such a easy task. So people at Roman time knew very much about this kind of construction. Okay.
Right. So then maybe on the specific questions that you have here. So, I mean, you're right. There isn't a lot of work on kind of graph transformation at the architectural level, but we did some work there, and there were other people doing sort of some work on modules or components for graph transformation system, but it's by no means established as in something that people would regularly do if they design graph transformation systems. Maybe it's a question of scale, because often we don't build sort of models that are so big that this is sort of urgently needed. But I'm sure, I mean, in some industrial applications, I mean, maybe we have to talk to Andy there. So he probably has systems that are sort of going on the hundreds of rules or something like that. So
this is too small, 100 of rules. I have further slides. If we are going to discuss this a bit, I can go a bit deeper in these questions here. And there are directions of how graph transformation systems could possibly develop.
Okay. Yeah. I mean, for my part, would be nice to see that.
Okay. If let's make the first round, and then if you are interested, we can go a little bit deeper corresponding to these three questions.
Yeah.
Are there further questions?
Right. So what I said. Okay. So on the first question, as I said, there are theories and concepts for components and modules, but maybe not the pressing demand from the application side at the moment. Maybe just because the scale isn't there at the moment to really need that. The second question I find interesting. So what do you mean by right? So parametric design, I kind of understand. So you can design a system with certain parameters, and so I can imagine you can design a graph transformation system with certain parameters and then instantiate them, and that gives you a concrete system. So I can imagine that. I don't think it's been done very much, but maybe people have proposed that I'm not aware of. Algorithmic design is even more intriguing. So having an algorithm that produces a graph transformation system, well, sounds like an interesting idea, but I haven't come across that.
It need not be completely automatic. So it can be only partial steps in order to support this. So these need not start with a generator by which you put in some specification and you get out a specific graph transformation system. Okay, but this I think we're discussing possibly afterwards, and graph transformation system, in my view, are only a part of the job. So for data specific and data intensive applications, but there are many other parts, and we have no idea how to combine this.
Okay.
Or not the necessary tools at the moment to combine this.
Okay. Sorry, I see a comment there on the chat. As I mean, we can read that ourselves, but if you want to elaborate or just explain what you want to say there.
Yeah, okay.
Feel free to unmute yourself and just.
Oh. This is again.
Hello.
Yeah, please go ahead.
I'm the one who put the chat.
Oh,
nice
fine.
to see you, Professor Nagl, after 20 years. I think this is really fantastic what you have done, because this allows for the conversation between engineers and software engineers in the way engineering modules are built, software modules are built and put together. And as you know, I'm aware of your Improve project. I'm Sab, even though my name, I think we have met in Aachen several times with Wolfgang.
Oh, yeah. So you are from Paris Tech?
No, I am from Carnegie Mellon. With
Carnegie, oh yeah.
We had interacted some long time ago. But the main point I'm trying to make is that the two important points you made is the relationship between longevity of process and history and collective memory that is stored in some forms, not only the objects, but also the transformations from one to the other and the compositions.
Yeah.
And this is something I think missing even in today's practice of engineering. Because of complexity, they have lost track of this basic set of principles you're talking about. And I think this is where the ideas you have presented and the notion of literally going back to engineering and say, here, I'll build libraries of things I know, how I built it, what I used it for, how can I extend it. That same principle pervades all of these activities. And I think that is what comes out beautifully in your lecture. Thank you.
Thank you. But I have to say something for the engineers. So I think this kind of approach only pays off if you are working for a longer time on the same subject.
Yes.
And whenever you change the technology, then of course you have to change this approach.
Yes.
This might be an argument. This is one argument that is not very often used in engineering. And the second argument that is not very much used in engineering is engineers are very focused in the way they build a solution which works.
Yes.
They are not so focused in the way they would like to learn from the last process to the next process what is new. Okay?
Yeah,
this is the opposite of people in informatics. They usually use new concepts, but never they finish a big system. So there is working with engineers is very interesting, and we could learn from each other.
I agree.
Yeah. Okay, now I go back in this. Here are the three questions again.
I think you have to share your slides again, Manfred.
Oh, I see.
Share your screen again, the window.
Do you see it again?
Yeah.
Yeah, fine. The first question is similarities in design between Gothic churches and graph rewriting. We miss, as we have said, the architectures. And the question is there an architectural graph transformation systems? So as we have seen it here, we have the level of the whole church, we have the nave, we have the travee, we have the wall, the form, the details, and so on. Do we have this kind of a refinement or this kind of a division in graph transformation systems? Big graph transformation systems have a lot of rules, and they all the rules invoke themselves in a specific way, or the user does this. Okay, but in order to do that, you must have different clear levels, and I think this is not very. So we, Andy Schur and myself, we presented some ideas in this direction, but not for graph transformation systems, but for the system by which you support graph transformation systems. That is easier, because there you can say, I have a central part which is modeled by graph transformation systems, and the other parts are put in the framework. And this, they have to do with taste, they have to do with coordination, they have to do with synchronization or whatsoever. All the rest, which is not graph transformation, is putting in some code which is stable and can be reused, okay? So this is the difference. I speak about to use this for graph transformation systems alone, okay? Then we must have an understanding of architectures, which I personally feel is not available. If somebody of you has seen an article which goes in this direction and graph transformation system, I would be happy to get the a link to this article. Okay. The next question is Gothic churches, informatics, and graph rewriting. So, do we use something like algorithmic, parametric, reuse design, design for classes? So, for very specific graph classes, for example, do we do that? Okay. And corresponding methods and tools. So algorithmic design, so the design is algorithmic or supported by an algorithm. The GTS graph transformation system at the moment, the design is not. There is no support at the moment. Okay. Or is the reuse aspect addressing graph transformation system development, that you make some library of reusable elements for specific graph classes, for specific applications, and so on and so on. It's also not the case. And this has to do with the question 3. We have to go to big examples in a certain area, and then it would be pay off in order to make such things. Or classes, if specific, more intelligent, is that idea known in graph transformation systems? So we have special classes. I think I saw once, it might be have been from Hans-Jörg Krajewski. Long time ago, I saw something which, so some kind of regular graphs, which were generated by a graph transformation system. So, for example, which around a circle, and every graph which is around the circle has a specific form and can vary this form and so on. For such kind of nice sketches of graphs, it might be possible to use these ideas. But again, if you have seen something in this direction, please let me know. Yes, and the third question in my, yeah?
Sorry, I was just going to say we have Pascal Legal on the call, and Reiko and I have seen something like this because there exists these topological manipulations of structures. And there you have, for example, a sponge being created, like some large structure which looks like a skyscraper with windows of some structure and so on. That exists. So I was just wondering if Pascal could maybe comment, because I think your team might be the closest to realizing something like this, no?
So if you have articles, Pascal, please send it to me. I promise to look into that.
Okay, I will talk with my colleague. He showed me a demonstration where he put some rule on he can build different size of a church with different so at least we could send you a demonstration on if he he wrote something. I will send you.
Okay, fine. So the most important thing, I think, is the last question, Q3. So, because of course we can, whenever we have an application which has a central part, which uses a discrete model and changes on that discrete model, we can use our graph transformation approach. But if I look, for example, if I would have tried to make the considerations not with graphic writing alone, then of course I get into problems. We have specific forms. We have very complicated forms. For example, a late Gothic tracery window. Okay, it's very complicated. We have relations between the different parts. There are constraints for the different parts. If you go to engineering, besides of the discrete part which is changing, you have differential equations, to have partial or linear differential equations, you have behavior of material, you have whatsoever, and all this has to be put together, and we have no idea how to do that. So this would be fine if we would study big examples where graph transformation systems is in the center, a central part, to model an abstract form of the system, for example, but also to make some kind of connections to those parts which are not really usefully described by graph transformation systems. For example, if you now make the nave higher or the aisle higher, then you end up with an extra restriction, because the big window at the top must either go or the light does not go in, and so on. And this is a problem. So layout, taste, constraints, continuous things. All these things do not work with graph transformation systems. This was an interesting discussion, which was initialized by Robert Milner at EasyGT 2002. It was in Barcelona. And I haven't, I'm not in the family at the moment, the center of the family, but I haven't seen anything which goes in this direction. There are steps in this direction. For example, Fujaba system of Albert Zündorf. He at least makes the connection to usual code. So whatever you have to put all these things you cannot manipulate by graphic transformation systems into usual Java code, and there you can make a connection. Okay. So these are the remarks I have. We should think about architectures. We should think about the third question, connections to problems which are not solved by discrete mechanisms for changing. Okay, how to solve that? And of course, as you have said, for the second question, you must have a problem which is stable for a long time, and you must work for a long time that these ideas make sense. We have discussed this for the question of engineering systems. Yeah, and if you look on engineering, if they make a new solution, for example, if you would have a package for solving, for example, constructing a car, and we're now turning to an electric car, you can throw most of it away.
Yeah. Okay, so yeah, thank you very much. So unless there are any further questions or comments on the last discussion here, I would close the official part of the seminar now, so we can all stay here and continue the discussion, but we will terminate the YouTube stream. So let me thank Manfred again for the interesting talk and the nice sort of connections that he made. And yeah, I don't know if you want to announce the next talk here. We have, I think, in 2 weeks, another one.
So in 2 weeks, we have Stefan Challa, who will be giving a talk. And yes, also from my side, many thanks, Manfred. And if anybody's still on a YouTube channel and wants to join the discussion, please do come over. I think we'll stay for a moment. And you can get the link by registering on the webpage. And thanks again. And thanks to everybody who participated. And I will now switch over.